This video is about the exponential function. We start off with an example. We're constructing a mathematical model of the population of rabbits on the well-known rabbit island. We start off with a really simple model. We start off with 100 rabbits on the island, and we suppose that every year 7 cute little baby rabbits are born. Very simple. We start off with 100 rabbits. At the end of the first year we've got 107, and 114, and 121, and 128, and so on. If we looked at a graph of that, we'd obviously see a straight line. We've got a linear function. But this is an unrealistic model. As we get more baby rabbits, as they grow up, we have more adult rabbits, and they will produce more baby rabbits, which will produce more adult rabbits, and so on. We'd have a more realistic model if we said that we have a constant fractional increase each year instead of a fixed number of baby rabbits. So if we said we have 7% increase each year. So this is how this works out, with the numbers of rabbits rounded to the nearest whole number. So in the first year we get 107 again, then 114 the year after that. But the year after that, instead of 121, we get 123 because we've got more rabbits breeding. And then 131, not 128, and so on. If we plot that in a graph, we don't get a straight line, we get a curve which increases more rapidly as the years go by. So we have the numbers for this, and we have a graph. It'd be nice to get some algebra, an algebraic representation of what's going on. So we start with, beginning of year 0, we've got 100 rabbits. At the end of year 1, we have 100 times 1.07, we have a 7% increase. For the second year, we have 1.07 times the number at the start of the first year. So we have 100 times 1.07 times 1.07. The end of the third year, we have 1.07 times that. And the fourth year, we have 100 times 1.07 times 1.07 times 1.07 times 1.07. For each successive year, we're going to multiply by another 1.07. So after x years, we're going to have 100 times 1.07 x times, multiplied x times. So that's 100 times 1.07 to the power x. So these are all exponential functions. 2 to the power x, 3 to the power x, 4 to the power x. In our rabbit example, it's 1.07 to the power of x. So we don't have to have just whole numbers raised to a power. We can have 3.7 to the power of x. Now it's not like x squared. X squared you might have met before. It's just a parabola. It's an example of a polynomial function, x squared, but it's not x squared, it's the way around. It's 2 to the power of x, not x to the power of 2. So, and in general, exponential function is some number to the power of x, n to the power of x. But we can have a bit of a problem with our exponential function when x isn't a whole number. If we have, for example, 3 to the power 4, well, we know what that means. It means 3 times 3 times 3 times 3. That's what we've already seen. But suppose you have 3 to the power of 4.1, when x takes on the value of 4.1. What does that mean? It doesn't make sense to say it's 4.1 3's multiplied together, because that doesn't mean anything. So we have a bit of a problem which we need to work out. And getting a meaning for that involves a bit of a detour. So the detour starts with something called the law of exponents, which you might have seen before. We look at an example, 3 to the power of 4 times 3 to the power of 2. What that means is that it's 4 3's multiplied together and also multiplied with 2 3's. So we've got 6 3's multiplied together altogether. In other words, we've got 3 to the power of 4 plus 2, 3 to the power of 6. That's going to work in general if we multiply together two numbers which are each of the form of some constant to a power. When we multiply them together, we can just add together each of the terms. So we have n to the power of a times n to the power of b is n to the power of a plus b. Very simple, you just add the powers. So a little example, 2 to the power of 3 times 2 to the power of 4 is 2 to the power of 7. We start off by thinking about what being to the power 0 means. It doesn't make any sense to say that we have 0 2's multiplied together, so we need a different approach. Now we try and find a meaning for it which will be consistent with the law of exponents. So we think about if we had 2 to the power 1 times 2 to the power 0, if the law of exponents still works, that's 2 to the power of 1 plus 0, so that's 2. So that means that 2 to the power of 0 ought to equal 1. Or at least if we say that it does equal 1, then the law of exponents still works for to the power of 0. Now obviously that will work for not just 2 to the power of 0, but anything to the power of 0. So anything to the power of 0 is equal to 1. We choose it to be like that because if we make that choice of meaning for it, then the law of exponents will be continue to be correct. Next, we want to have a way of dealing with a situation where the power isn't a whole number. So if, for example, we had 4 to the power of a half, what could we make of that? How could we calculate that? We can't have half 4's multiplied together. Again, it doesn't make sense. But we need to find a meaning, and again we're going to find a meaning which is going to be consistent with the law of exponents. Suppose we have 4 to the power of a half times 4 to the power of a half. Now, if the law of exponents is retained, that's equal to 4 to the power of a half plus a half, so that's 4 to the power of 1, so that's just 4. That implies that 4 to the power of half is the square root of 4, because if we multiply it by itself we end up with 4. So 4 to the power of half is square root of 4, which is plus or minus 2. More examples of this. 9 to the power of a half will be square root of 9, so that would be plus or minus 3. 8 to the power of a third, well, if we multiply 3 of those together, we'd end up with 8. So 8 to the power of a third is the cube root of 8, which is 2. 2 to the power of half is the square root of 2, which is not a whole number, it's plus or minus 1.414 approximately. And in general, a to the power of 1 over n is the nth root of a. That's the number we have to multiply together, n of them, and we end up with a. Next we're going to think about what happens if you get the power of a power. So if you had, for example, 4 to the power of 3 to the power of 2, what does that mean? Well, we already know really. 4 to the power of 3 to the power of 2 means 4 to the power of 3 times 4 to the power of 3. And by the law of exponents, that's 4 to the power of 6. So we get the 6 from the 3 times the 2. Another example, 4 to the power of 3 to the power of 3 means 3 lots of 4 to the power of 3 multiplied together. So again, by the law of exponents, that will be 4 to the power of 9. And 9 is 3 times 3. So in general, n to the power of a to the power of b is going to be equal to n to the power of a times b. That's really following from the law of exponents. Next question is, what happens if the power is a rational number? So we have a reminder, what is a rational number? It's a number of the form a over b, where a and b are integers. So that, for example, we're asking, what does 4 to the power of 3 over 2? What does that mean? How can we work that out? So 4 to the power of 3 over 2, that's the same thing as 4 to the power of a half times 3, and that's 4 to the power of a half to the power of 3, and 4 to the power of a half is 2. So in fact this is 2 to the power of 3, so that's equal to 8. So we've got a way of working out 4 to the power of 3 over 2. So in general, n to the power of a over b is n to the power of 1 over b to the power of a. In other words, to work it out, we find the bth root of n, and then we multiply that to the power of a. Finally, what happens if the power is negative? If we are asking about 2 to the power of minus 1, how can we work that out? So suppose we try and work out 2 to the power of 1 times 2 to the power of minus 1. Now if the law of exponents is still to apply, that's equal to 2 to the power of 0, and we've decided that should be equal to 1. So 2 times 2 to the power of minus 1 equals 1. That implies 2 to the power of minus 1 is equal to 1 over 2, and there's a half. So in general, n to the power of minus b is equal to 1 over n to the power of b. So by making the law of exponents to be consistent for lots of different powers, we've been able to find a way of working out a number to another power for lots of different situations. So we can calculate a to the power of b, where b is any positive or negative rational number, and we can also do it for any positive or negative real number, because we can find a rational number which is as close to any real number as you like. This is a case where a is any positive real number. We haven't done it for the situation where a is a negative number. So for example, minus 1 to the power of a half. How do we calculate that? Well, we have a problem with that. That's the square root of minus 1. And we can't find any real number which is the square root of minus 1. We need to go to imaginary numbers for that, but that's something else altogether. So now we can calculate the value of 2 to the power of x for any value of x. So we can plot this graph properly and we'll get a shape like this. So this goes through the point 0, 1, because 2 to the power of 0 is equal to 1. If x is negative, then the value is going to be less than 1. So for example, 2 to the power of minus 1 is a half. As x gets larger and larger and more negative, 2 to the power of x gets smaller and smaller, but it never gets down to 0. It approaches 0, but it never gets there. So that's an asymptote, in fact. As x is greater than 0, the 2 to the power of x increases. 2 to the power of 1 is equal to 2. 2 to the power of 2 is 4. As x increases, it increases more rapidly. In other words, it's concave upwards. The rate of increase also increases. And all exponential functions are this general kind of shape.